everyone. Okay, good luck with that. So here's what I will talk about. Not all today, so I have another lecture tomorrow, and what I don't manage today, we will, do the rest tomorrow. And then I will also talk a little bit about particle ID. So what I will try to cover today is a little bit remind everyone about the basics of particle detectors, what really this is all about. And then I will start to talk a little bit about the various detector types and what you should keep in mind about these tracking detectors, calorimeters, particle identification, and more. And then we come to the EIC. And when you build a detector, the first thing you have to think about is what you actually want to do. What are the requirements? How good does the detector have to be? What does it have to do? And then we'll talk about this. And then we talk about the design of the EIC, which was a very wild ride, and it's still to some extent also happening. And then at the end, I show you actually where we are and what are the detectors and how it looks like and how complex and complicated it is. Okay, so a perfect detector. So how would a perfect detector would like? It would detect all kinds of hadrons, charged hadrons. It would detect neutral particles, photons, neutrinos. It would perform particle identification. We could determine the 4 vectors for all particles that are produced in 4 pi. And we do this at whatever megahertz interaction rates. And it withstands high radiation, doesn't matter. And unfortunately, a thing like this, while a pizza can have all the different ingredients you can imagine, it won't work with the detector. Building detectors is unfortunately very much about compromising. And this is a little bit what I will try to kind of explain to you where we are making these compromises. So detectors are made out of matter. And if you have to detect a particle, you must interact with matter in some way. And of course, the interaction and what dominates depends very much on the particle type. And the energy level strongly depends also on the energy. So if you think about hadrons, hadrons dominantly interact with the nucleus itself. The electrons don't matter so much. They have an effect. We will talk about this, but for hadrons, the key is the interaction with the nuclei. On the other hand, for electromagnetic interaction, here very much it matters also what the electron does around the nuclei. You also interact with the electrons and of course also with the nuclei. And when you talk about weak interaction, then also electron nuclei. So that is a very simple picture. So let's move on how this really works. One of the key things you should know, even if you're a theorist or something, the Bethe-Bloch formula should be in your head. And the Bethe-Bloch formula describes the mean energy loss, the EDX, of a particle, a charged particle, usually baryons and mesons, that traverses matter. Okay? For electrons, it looks a little bit different because here there are radiative effects which dominate, and we will talk about this a little bit later. But it is really Bethe-Bloch for hadrons. So this is a very complicated formula. What really matters is the incident particle, the charge, the velocity, and the mass. And then you have your absorber, the material, where you have ZA, and some numbers which have to be measured, like ionization potentials and all that stuff. That's all not so important. I want you really to focus on this thing here on the top, okay? Yeah. So how does it look like? This is the Bethe-Bloch formula. This is the energy loss, essentially, or stopping power, as a function of the momentum. This is here for muons, could be pions, would look very, very similar. So there is first key point, which is this lowest point. That lowest point is roughly at a gamma of 3 to 4 for most particles. And that we call the minimum ionizing particle, or MIP. Experimentalists, you very often hear them about, oh yeah, that makes a MIP. Can we see the MIP? That is what it is. It's the minimum ionizing particle. And it's usually in the range, mostly we are dealing about. It's kind of like, from whatever, 10 MeV, 100 MeV up to a couple of GeV. What you see, if you go higher up in energy, there is a small increase here, but relatively flat. And then you go up this curve here, and that goes with 1 over beta squared. ddx 1 over beta squared. And then in real life, simulations unfortunately never really included that. The OGR3 simulations never included actually this thing here on the top. That is the Bragg maximum. What is it important for? Any idea? Anyone?
Tell what particle it is based on how
what do you use it for mostly? Where in our life is the Bragg maximum super important?
Need some sheiks again. Therapy.
Cancer therapy, right? Because what you want to do is you want to shoot the proton or the ion in the body such that the Bragg maximum is exactly where the tumor is. You want to hit the tumor exactly at the Bragg maximum. Because if you hit it later, it destroys the tissue before or the tissue after. You want to optimize that. That is where beta block comes into the game. Okay, continue. What is the basic idea of detectors? Really the large majority of physics detection processes is known since a very long time. The principles are always the same, and they are based mainly on the electromagnetic interaction. There's ionization. Think about this old good ion chamber. You have like a condenser, the anode, the cathode. You have some gas in between. You shoot a particle in between. It ionizes. The electrons and the protons go to each plate and create a signal. Ionization. Scintillation. Scintillators, you all have seen these plates, this transparent plates. These are scintillating materials. A particle goes through, a photon goes through, they excite the material inside, and the material then usually transmits a lot of light in terms of low energy photons. Now, how we detect photons? In the good old days, we did that with photomultipliers that have here a photocathode, then a focusing electrode, and then you have here these diodes. They hit the first one, they create electrons. They hit the second one, and they create more and more electrons until you have a very strong signal which you read out. Those are hardly used anymore. We have silicon photomultipliers and other things, but the principle is still somehow, there. And then we have Cherenkov detectors. And Cherenkov light is emitted when a particle traverses a media with a larger velocity than the velocity of light in the medium. And that gives this light. We all know it when we see photos of reactors, this blue light coming out. This is Cherenkov. But the cleverness and how to design detectors really lies in the way how you can actually make use of these. And electric signals, you have to collect the charge, and optical signals, you have to collect light. And much progress in the detection of particles in a couple of last 30, 40 years is really by the progress in the electronics. This is where we really, really made progress with low noise electronic, more sensitive, faster. And this is where the fun is. I want to come to a couple of tracking issues or detector concepts. So now let's start with the tracking. What do we mean by tracking? By tracking means, we're not tracking a dog. You don't want to know where he goes. Well, but what we want to know is what is momentum. It's 3 moments. Tracking is all about the 3 moments. Well, what is the recipe? You need, of course, measurements as accurate as possible of the XYZ positions, and you need a magnetic field of some sort. There are really only 2 sorts of magnetic fields right now, really heavily in use in high energy and in nuclear physics, other than dipole. And the first is the solenoid. This is, of course, a large homogeneous field inside the coil. The fields go around here. So you have wires wrapped around this way, the blue, and then the field lines are homogeneous, mostly inside. and there's nothing else inside. So we have a big volume with field. The problem is the outside magnetic field you don't want to have in your experiment because it's electronic. You want to stand next to it. You don't want your credit cards to it. So that's why there are usually return yokes, big iron, which then guide the take up the magnetic field. So if you want to build one, you have to look at the cost. The cost sits mostly in these wires, superconducting wires. So the cost is proportional to the length. It is proportional to r squared, to the radius of the magnet, and to the magnetic field. Okay? That's what you have to cover up. In terms of physics, what you're interested in is the best possible resolution. And the resolution depends on of course, PT, but it goes inverse with B. So if I double the field, I have double the resolution, or half the resolution if you want. I improve the resolution by a factor of 2, but unfortunately, I increase the cost by a factor. If I increase the radius, then let's say by a factor of 2, then I have a 4 times better resolution, but also 4 times the cost as before. So if you want to build a magnet, if you ever want to design an experiment, make it magnet large, big radii. So the absolute coolest thing is a toroid. There's only one experiment right now you probably all know, which is Atlas at the LHC, that has a toroid. It is a relatively large field over a large volume. It is non-uniform. Field lines goes like this. It's very complex because you have these coils stacked around it, but it is in principle ideal for a 4-pi detector. And we looked at that initially for the EIC. That was not a bad idea, but it turns out that you have to have these pipes, the wires essentially, going very close to the inside. And that is not something you want because you put a lot of material in the center of your detector. Atlas essentially has a toroid only on the inside, and they have a solenoid also on the inside, toroid outside, to kind of work around this problem. That's why Atlas is also such a humongously large experiment. So, what are your choices? You can place the coil in front of the calorimeters, which you use to measure the energy. These are usually the last detectors outside. Or you can put it behind the electromagnetic or hadronic calorimeter. So if you put it very much outside, so like the last outside detector, you have a very large magnet and a very large price tag. If you put it in front of the calorimeter, you have the problem that the magnet also has a mass. And you're kind of harming the quality of your electromagnetic calorimeter. Now, there's a lot of R&D going on to build very thin conductors and even use honeycomb structures for that. But that is not very far. And one of the reasons is that the industry itself is not very interested in very light magnets. Yeah, the majority of R&D on magnets goes into MRIs. There are thousands and thousands of magnets produced. If they are super light or not, really doesn't care for them. On the long term, I think the development of high temperature superconductor will bring a huge improvement, but we are unfortunately not there yet. So, what are the magnets around in the world? Just to give you a little bit of feeling. So LHC has, of course, CMS, which has the absolute monster magnet. That actually took quite a while to build and almost ruined the company who was promising to build it. That is a 4 Tesla field, enormous, and the radius is 3 meters. It's an absolutely big magnet. Then we have LHC, we talked about this. What our friends in high energy physics for this Higgs factory, which we call now FCC, if it is built at CERN, have in mind is something in the order of 2 Tesla, but also very large. A radius here of 3.7 meters and a length of 7.4 meters. Enormously large magnets. The reality is, and we looked at this, there is no company in the world right now who will build you a large magnet, let's say in the order of 2 meters with 3 Tesla. There's just no company. because these companies build that thing only once, right? Just for some physicists, can you build me one, please? If you would say build me 1,000, then they would listen, but one is not, because it's a huge effort. So this is not going to happen. This will be a real fun thing, how the FCC on the long term is going to build their detectors. Now, let's have a closer look at tracking. So the momentum resolution is key. And at high momentum, this is really only determined by the resolution of your device, mostly, okay? So this is the precision term. This is somehow the resolution, delta PT over PT. By the way, this is a formula which was calculated by hand by Brook in 63. And I'm always puzzled when these numbers suddenly pop up. There's square root of 720 over n plus 5. Where in the world does this 720 come from? But it works. So it's actually de facto. So what you see here, it depends on the resolution. That means if you have a 5 micron pixel detector or a 1 millimeter pixel detector. That is what really matters here. This is the lever arm, and this is naively clear, right? I mean, if the more I measure from the track, the better the quality is. And that goes with square. The magnetic field, the higher the magnetic field, the better the resolution. And then there's this funny factor n here, which is the number of hits you have, okay? So that all matters at high PT. At low PT, we are completely dominated by I'm getting there. We are completely dominated by multiple scattering, okay? Like scattering in the material. And there's not much we can do. At the end, what you really measure is, of course, both. So you have to add them in quadrature. So that is what you measure. And you see that very nicely here. Here is your multiple scattering term. Here's your measurement term. And that is the total error. That is this is the relative error. Okay? So this is how it looks like. And you have to optimize this. You can only optimize that term by reducing the radiation length of the material, making it thinner, less mass. That's what you need. And that is, at EIC, we looked so carefully on having as little mass as possible in the load system. Okay. So how do you make resolution great, good? Well, you can have more hits. Okay, you see that here? No. Yeah. But it goes with square root over n. Not so much. And especially the more measurements you have to have detectors. That means the more material you have, which goes again in the multiple scattering. Now, increasing this one here, that guy, that's cool. That you want. That's good. But the finer you have, the more channels you have to read out. And at some point, we are at the EIC at that problem that we almost don't know where to put all these cables. Okay. You want always to reduce the material. But again, that also means reducing sometimes n. The longer it is, the better, but it needs room, of course, for a detector. And the higher the magnetic field, the better. There is a problem. In a magnetic field, the tracks curl up. If you're looking for a process with low PT particle, they will curl up. You don't measure them really, right? So essentially, if you have too strong a magnetic field, you make a cut and you cut away a lot of physics. So, all this has to be optimized. Let's come now to one of the few detectors which actually destroys your particle. Okay, it's a destructive method, and that is calorimetry. And what you simply want to measure with calorimetry is the energy of a particle. Dump a particle in some block of matter, and it goes away, and you measure essentially whatever it produces, and that tells you about the energy of this particle. It's a destructive method. We distinguish between electromagnetic and hadronic calorimetry. And typically, the detector response is proportional to the energy. This is not always true for hadronic showers, but it's roughly, okay? And the energy of the particle is, of course, converted into ionization and excitation of matter. And that is what you're trying to measure. So let's talk about electromagnetic calorimetry. Here's a picture of a shower from a simulation. So there's a couple of processes which affect electrons and photons if they hit a calorimeter. There's a photoelectric effect, there's a Compton effect, there's pair creation, ionization, Bremsstrahlung. And they all add up in a very complicated way. For those of you who have the particle data booklet, you can look it up. And you see these graphs, which process dominates at what point. Bremsstrahlung usually, a pair creation is at higher momentum and so forth. The key, what every physicist should know, the key for that is the radiation length. The radiation length is defined as the distance over which the mean energy of an incident electron is reduced by a factor of E. Okay? That is the key thing. Here, actually, that plot, I hope you can see it, is a little bit small, I'm sorry. So this is the energy deposited of an electron as a function of the depth. Okay? And so a 1 GeV electron, you see kind of like after 10 centimeter, is the maximum. After essentially 20 centimeter, all the energy is dumped in there. However, as you become more and more energetic, here's the TeV, here's 100 GeV, you will see that you need a longer and deeper electromagnetic pulse. That is why at LHC they have quite some radiation length in the electromagnetic calorimeter. So typically 10, 11 is something radiation length, what calorimeter should have. Now we come to hadronic calorimetry. So you have a baryon or a meson which dumps into a hadron calorimeter. There's a lot of excitation of nucleus breakup to produce secondary particles. And what you have are hadronic showers, and they are very white, and that's an issue. When I compare here between this is a photon shower, an electromagnetic shower, which you see is very focused. And this is hadronic shower, which you see is very broad. And that, of course, has something to do then also how you segment your calorimeter. The hadronic showers are typically 10 times wider and deeper than electromagnetic showers, which tells you that an electromagnetic calorimeter can be a little bit light and, swift. But hadronic calorimeters are usually, tons and tons and tons. The key here is not the radiation length, but the so-called interaction length, which is the mean free path between nuclear collisions. So these are the two variables. Lambda is the key parameter for hadron calorimetry, and lambda, the radiation length for electromagnetic. So what are the types of calorimeters? For electromagnetic calorimetry only, we are using very often scintillating crystals, glass blocks. So these are homogeneous. It's just a block, okay, of something. Photon comes in or electron makes light, and we collect it somewhere at the end. It's one big block. The best of all the crystals and you can use is lead tungstate crystals. You just don't get them. Making them is really an effort. So for CMS, they had this lead tungstate calorimeter. They used a company in Russia which halfway went bankrupt because they underestimated the price. That just didn't work out. There's right now only one company in the world, which is called Kryto in the Czech Republic, which actually hired the Russian engineers from that company. And they make very good crystals. We tested them. There was another attempt in China, but that didn't work out. There are other crystals like level L3 at lab had PGO crystals and God knows what. So, but here's just a picture so that you see the idea is very simple. You have just a glass-like, quartz-like crystal, and then at the end you read that out. You can't do that for hadron calorimeters, and that is why usually we have what we call sampling calorimeters, and they look like this, that you have some thick absorber, usually iron or steel, and then in between you have scintillator blades where you read out the light. This way you can make it very heavy, without, having too much to measure. So you sample in between, and that gives usually a very accurate measurement. Nevertheless, the best electromagnetic calorimeters give you a resolution of 2% over square root E, and that is with the tungstate. Hadron calorimeters never get there. The best hadron calorimeter ever built was the one from Zeus at Hera in Germany, DAISY, for EP collisions, and that was 35%. But typically they are between 40 and 100% over square root E in terms of resolution. The resolution is measured this way. The first is the stochastic term. So when I say 2% or 40%, this is 2% or 40% over square root E. But there is a constant term. Forget about the noise term. There's a constant term. So if you want to impress someone, if you have no idea about hardware, you're sitting in a calorimeter talk, and then if you want to ask some sensitive question, ask what the constant term is, because that is the most tricky one to deal with. This constant term comes from inhomogeneity. It comes from bad calibration and nonlinearity. And the people who build calorimeters, they have to live with that, which is given by their technology, whatever they use. But that is on them, okay? The better you work, more accurate, and the more you think about it, the lower this constant term gets. So that is a little bit an art form to get this as low as possible. Good. Yeah, particle identification. I will talk about this tomorrow in length, so I want to keep it short. But what does it mean, particle identification? So we have the 3 momentum, but we want everything. We want the 4 momentum. For that, we need the mass. Okay. And how do I get the mass of a particle? Well, if I have the momentum, the only thing I can do is measure its velocity. So essentially, PID means measuring velocity to a large extent. Or you can also measure energy loss, and I will come to that. There's time of flight. We are talking about Cherenkov detectors, and we have to talk about transition radiation detectors. But the trick is that different momentum ranges requires different technologies. So let's look at this axis here. That is the momentum of the particle. And here you on that axis, you see the required detector length, okay? So this is here already a meter. That is 10 meters. That's a bit iffy already, okay, for a detector. 10 meters radius is like, I think that doesn't even exist. So one thing I can do is I can measure the time of flight, how long a particle needs from A to B. If I have 10 picosecond resolution, which no detector in the world has right now, we are working on it, but we are not there. Then you can get up to, but let's say up to a meter, you can get up to 2-3 GeV. That's it, not more. What you have to do if you want to go to higher momenta, you have to go to Cherenkov detectors. That is the key technology in the high BT range. And here, and I will talk tomorrow about it, it very much depends on the radiator what you have. If you have crystals or a liquid, you typically sit here. If you have aerogel radiators, you sit here. And then only if you come to gas, you really go to the very high momentum. Who of you knows what aerogel is? Have you ever seen aerogel? It's absolutely, if you have seen, it's absolutely cool. So this one, it has optical quality, so it's transparent. You can look through, and it's light as gas. It weighs nothing. You don't even know that you have it in your hand. It is used industrially in lower quality for windows as an insulation very often. But that is crap quality we cannot use. There's at the moment, because aerogel was typically produced in Russia, that is, of course, out of the question right now. And the only source we have is one university in Japan who makes it. That's the only source we have left. Aerogel is good. At CERN, we found a block. It's pretty expensive. So we found a block lying around, and we made hearings for our girlfriends, not knowing that the moment it rains, they need salt. That was a bit of a bummer. So, but yeah, so aerogel is a really fascinating material. If you get your hands on, you have to see it. It's Looks like glass, but it is the lightest material you ever have in your hand. So, okay. PID with DEDX. Those of you who work on ALICE or STAR or S-Phoenix or all these detectors which have big gas detectors know these kinds of plots. This is the momentum scale, and this is the energy loss. You see these different bands. This is the proton band. This is the electron. The electron goes along here. Ugh, this thing is really bad. And then you have deuterons and so forth. And that works, as you can see. You can probably identify those up to, let's say, 1, 2 GeV. But the moment they cross, it's over. There's nothing you can do about it. And so the art is really to make these bands as small as possible. And that means you have to have very good DDX resolution. DDX is not so commonly used in silicon detectors. And the reason is very often that silicon detectors are not reading out any energy in the pixel, but very often just binary, hit or not hit, 0 or 1. Okay. 8-bit silicon detectors are not very common, which is what you probably need for a serious one. And the other is particle ID with time of flight. I mentioned that. That is pretty cool. So the time is measured, and the time is just the path length of the particle divided by its velocity. So as you know, momentum is gamma times the mass. So you can calculate the mass simply by having the momentum measured, the length of the track, the time measured, and that gives you. The tricky thing with that is that this mass depends on the resolution of the momentum, the resolution of the length, how well you know the length of the track, and the resolution of your time. And tomorrow I will tell you that there are 2 times, namely the start time and the stop time, and that is pretty tricky. Okay. Then we have PID with Cherenkov radiation. The charged particle travels faster than light in medium. Then it emits this Cherenkov radiation in a cone. We can, for high PT, usually have a radiator which is gas. On medium PT, we use aerogel, and for low PT, we can use quartz. In EIC, we use them all. And tomorrow you will see the whole glory of it. What is always the key? The key for that is, like I told you, if you're talking with a colorimeter guy, ask him for the constant factor. If you talk with a Cherenkov guy, ask him how many photons you get, because that is really tricky. There are not many detectors, especially this ring image Cherenkov detector, I will talk about this tomorrow, where the number of photons is 10 and 12 and 12 and 12 and 12 and 12 and 12. You easily lose 2, 3, and then suddenly things become very iffy. Then there is a Dirk. We'll talk tomorrow about it. It's an ingenious detector. And then threshold counters. The other thing are the transition radiation detectors. And don't quote me ever about this. I'm not aware of any transition detectors that ever really work well. It's a real pain, these detectors. So the idea is that you have a particle that traverses mediums with different dielectric layers. So between vacuum and let's say some glass. Very often what they use now is just foam stuff, or this fiber materials, because there you have a little bit air, and then you go through the fibers and so forth. And during this transition, they emit photons, and their photons are emitted very close to the track at an angle of 1/gamma. So they are very close, and there are not many. Typically, the energy is very low. So you have to use low Z material, preferred to keep the reabsorption small, because they are low energy. They could be absorbed again within that. So I think Alice has a TRD. We did R&D for EIC also and on a TRD, but at the end decided to use it. So now we put it all together. Now we have,
I have a question about the transition radiation.
Yeah.
So like from an E&M perspective, I can see why if you have a charged particle going through a change of the electron, it emits photons, of course.
Yeah.
But how does it work on a particle level? The change.
Oh, the TRDs are mostly used for electrons.
Okay, so
That's just, this is for electron ID. Yeah. You would never use a TRD for anything. So let's put it together. This is how a detector usually looks like. That's it, okay? So you have your beam and you start with tracking detectors. If you want to know about the vertex, like charm meson, switch decay or something, you have to be very close to the interaction point. So this is the first step. You have to start with tracking. Typically then comes particle identification. And now you have to keep this, of course, at low material as possible. Now typically comes the electromagnetic calorimeter to measure photons and electrons. You don't want to move that very far out because they have to traverse all this and they probably lose energy already, not the photons, but the electron. So they are usually measured in electromagnetic calorimeters. That's the purpose of an EM code. Then you have to have the magnet because you have a field to make the tracking possible. So the tracking has to be always inside the magnet. Now, hadrons, neutral or charged, of course, the charged hadrons are participating in the tracking in the PID. They even leave a signal in the EM call, while neutral particles go all the way through and they're only absorbed in the H call. If you want to measure a neutron or K0, whatever, that only works if you measure it in the hadron calorimeter, which unfortunately, as we know, doesn't have a great resolution. That's a little bit a protector problem. If you want to measure muons, as you know, go through everything, and this would be then at the very end. Muon detectors are always at the outside. Yeah.
What about the PID for neutral particles?
Nada. Not much. Really not much. PID for neutral particles very often is done through their weak decays. If you think about a lambda, has this typical V structure, so you try to measure the end products, the decay products, if you're lucky. This is a little bit a problem, these neutral particles, because especially if you measure jets, because there's a fraction of the jet energy which sits in neutral particle like neutrons. And so if you do not have a hadron calorimeter, you do not know what this component is. You can correct it, you know, empirically or with simulation roughly, but that is something you don't get. It's really hard. I mean, the only way of PID for neutral particles is really in hadron calorimeter. Yeah, so now we all only have to wrap it around and we are done, right? Not unfortunately. So what is about the EIC detector? Let me talk in the last 15 minutes about the EIC detector. You start with the big questions. And don't think about this as lightly, because that took us almost 10 years. These have to be questions which matter, so that you can sell this, that somebody spends $3 million for that thing. Okay? That better be a good question. Okay? And then you have to make your physics case. So by the way, this was done. Shoot, go back. Don't you love animation? So, the physics, the big question, if you want, were actually discussed at an INT workshop in Seattle, which lasted several months. And that was a very important one because we not only laid out the physics case in our mind, but we also set priorities. What is more important? What is less important? So we had these golden measurements and the silver measurement and so forth. So then we wrote the white paper, which I think lays out the key of the whole EIC. And at the same time, we started very early with generic R&D. That means we called people and they came to Brookhaven and we gave them money and they started to do research. At the beginning, there was not much guidance. So people, it was like Wild West, you know, I said, I have a great idea. And they went ahead and we gave them money. And it had a different, there was a different idea, and that is to create a community with that. That people meet twice a year, talk about their work on a detector. And it turns out that 90% of the people who now build detectors and are in this detector collaboration for the EIC come out of this program. So it was very successful in that sense. Once you have that at some point and you become serious, you have to sit down and define your requirements. So you look at all the processes, what you want to measure. You have your theorists to give you all these great ideas. Then you hope that you have a generator which gets that. And then you say, aha, I have to measure pions in that range, in that thing, and so forth. And you have to really write everything down. This we did. This was a 1 year, it was the most impressive large effort I ever worked with. We had 400 authors from 121 institutions, and we worked for a little bit more than a year. We had meetings and meetings. It was enormous. It was a really huge effort. And we got this yellow report together, and I'm very proud of this. This was an absolutely fantastic effort. And in 2001, we really published that. And the Department of Energy is that also, that is their Bible. If you want to build an EIC detector, look at that. So now that you know what you roughly want, then you have to be a little bit more targeted in your R&D. You cannot just get something to have fun, but you really have to focus on what is important for the EIC. And then we start to design. That was actually, this was drawn here. This was Tom Hammick. That was the first picture of a detector, actually. And they were, scribbling this thing. And he took a photo and sent it to me. I'm really proud of this photo. So that was the first time you get an idea. People thought about how to build that, okay? The other thing you have to do is every time you have a design, you have to do simulation and performance evaluation, which is easy to say because you need the software for that. So although your detector is continuously changing, you need some software for these detectors to do the simulation, and this is not an easy thing. And that is very intensive. And then you iterate, you go over and over. You have a new design, you test it, you do more R&D because you don't know how to build it, and so forth. And either you run out of patience, money, or both. And I think we run out of patience at some point. and this is where this detector comes from. This is the final baseline. That is epic.
What's the size? How many meters?
So that here is 9 meters. Unfortunately, I come to that because this is all we have. The length is now a little bit more relaxed. This is 2 meters, 3 meters, maybe here outside. So the inside is roughly a meter here. Radius, sorry. So the reason, you heard the machine talk, right? There was a machine talk, right? Okay. So the machine people had a great idea of having, so you have the hadron ring, which is for protons or ions, and you have the electron ring, right? Which is for electrons. But it turned out that you cannot maintain the polarization of the electrons this way. So there was a third ring, which was also in the tunnel, which was called the RCS, recycling something synchrotron. So that tunnel, that small tunnel, had 3 rings in there. And now you have a problem because on your detector, you need the electron ring and you need the hadron ring, but now there's a third beam pipe. And that beam pipe has to go around the detector. And you cannot go too much around because these are electron and synchrotron radiation. So, and that determined our lateral dimension. Luckily, this is now gone because they built a separate ring here. And that makes our life a little bit easier because now we can grow if we want laterally. And I lost my, here. So, okay. Move on. So what do we want to measure? The things which, of course, Fred is interested in is our PDFs. That comes from the reduced cross-section, from the structure functions, if you want. All Fred needs is the scattered electron. Because as I have learned or will learn, the scattered electron gives you X and Q squared. And the cross-section, of course. So here you want to bin as fine as possible in X and Q squared. For semi-inclusive DIS, of course, you have the scattered. whatever you do in DIS, you need a scattered electron. If you don't have X or Q squared, it's a useless event. You can throw it away. Okay, so that is key, that you always have to have. Semi-inclusive deep inelastic scattering means that you measure some of the hadrons produced. Here you have 5-dimensional bindings. And of course, the crown is exclusive processes where you need to measure everything. So you have to have a hermetic detector. There are not many hermetic detectors in this world. At LHC, none of them is hermetic. They have mostly in the barrel. Now they're adding here and there in the front and in the back, but there's nothing hermetic, and we have to do that. And that is a real challenge. The electron is the key. Yeah.
Is it actually possible? I mean, physically possible to have
I mean, you have to. Yes, yes and no. You will see. Keep that in mind. Okay. I mean, no, because there are cables which have to come out at some point. You know, it's right. That's what I said. You have to have compromise, but you try hard. So the electron is tricky. Okay. So you all know X. Here's X. That's the fraction of the parton which you scatter on. The interesting region for saturation, where gluons dominate, is the low X region. That's here. That is Q squared. That is the resolution, if you want, the virtuality. Think about it as a resolution. Okay, the higher Q squared, the better the resolution. So, where do the electrons go if I measure here? Okay, and if you look at this, when I did this simulation for the first time, I was really kind of freaking out. So what is this diagram? That is really the angle. So the electron comes in here and scatters. And you see it scatters in this direction. And that is the momenta. So you see they have almost momenta from 2 GeV up to whatever, in this case, 20 GeV, because it was 20 GeV on 100 GeV. That was the collision, okay? And look where they go. There is no way you measure that with the central detector. They go essentially along the beamline. You lose them. Some of them are even in the beamline. That sucks. So now I go a little bit to larger X, and we are improving slightly. You see that things grow a little bit. Now, if I'm going up in Q square, then things improve a little bit. And you see -3 to 3, this is very well now in the central detector. It's in the forward end caps, but we can do it, okay? And then if I go to 4, even then, we are not really at mid rapidity. And only if we go to the highest, largest Q squared and the largest X do we find activity in regions which those of you who do Alice or heavy ions or PP collision and hadron colliders, that is your region, right? The mid rapidity region. But what I want to tell you here is that this is a little bit different in DIS. Okay. 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 So what do we need for measuring this electron? You need excellent electron identification. So you have to be able to distinguish an electron from a hadron. And you do this usually with calorimetry. You need even rapidity coverage for tracking and calorimetry, because that has to be covered by calorimetry and that by tracking. You have to have a low material budget to reduce Bremsstrahlung, because Bremsstrahlung is the natural enemy of the electron. And you have to have a very good momentum and angular resolution. This is really critical for the electron. So, PID. Now, this was kind of the blow. That is a tough one. So, this is Prithia event generator, 18 GeV electrons and 275 electrons. These are all hadrons produced. This is the rapidity. This is the electron end cap. This is the hadron end cap. Okay. So what you see is that K, pi, pre, they're all, you know, sitting roughly around 10 GeV here, up to, let's say, the forward region where the hadron goes, up to, let's say, 2 to 5, and then it goes up to 50 GeV. So you have to cover all that. That was the requirement. And no detector ever has faced such a problem. as you remember, CMS and Atlas don't even have particle identification. LHCb has some, Alice has some, but you know, in high energy physics now, this is completely out of the question. And we have to do this. So this is a very tricky thing. Here I add up all the requirements. I just want to emphasize, we have to measure as much as possible. So from -4 to +4 in rapidity. We need, especially in the backward region for the scattered electron, the best possible resolution. And we need PID up to 50 GeV. So, and then you sit down and you think, how do I do that? So then you go to the machine people and said, what magnets can we put in? And here's the trick. Electrons, the moment you bend them, they produce synchrotron radiation. When HARA-2, there was an upgrade to HARA, switched on the detectors after the upgrade, both detectors went black because of the synchrotron radiation, which they have not shielded enough. It took them a year to fix them. So the machine people, the designers of the EIC, said very clearly, we are not bending the electrons. In the region around the detector, the electrons will go straight. And you are not using any magnet which bends them in any shape or form. And that leaves only one magnet, namely a solenoidal field. That's all we can do, right? I mean, for example, in the forward region, you would love to have a dipole, but that bends the electron. And then we have also, for environmental reason, people set a limit of 30 megawatt synchrotron radiation. We cannot emit more than 30 megawatt. 30 megawatt, by the way, you can lighten up a small village with that. It's enormous. So, good. But now you are running into big trouble. In the central region, that's good. You know, you have the full magnet, you know, you can bend it. But in the forward region, at some point, your magnet runs out of bending power, because for tracking, what you need is B times DL, EDL. And you don't have this. They are not bending enough in the forward region, which means you have to put a lot of emphasis on colorimetry and not so much on tracking, because you don't kick them enough anymore. And there's nothing we could do. So this is kind of the story. You have to have a central detector. There's a lepton end cap, hadron end cap. Here in this picture, electron comes from here, proton or ions come from here. The scattered electron luckily only goes, you know, up to the central barrel. The lepton end cap and the central detector have to measure the electrons in the hadron end cap. You're not so interested. The hadron end cap takes everything of the hadrons, because the hadron beam comes in here, it scatters and sprays in here, okay? So what you have to do is, of course, and we talked about this in this simple diagram, you have to have vertexing, tracking, PID, EM-cal, the magnet, and H-cal. And you have to do this not only in the barrel, you have to do this in all directions. But then you have the problem that you have important physics in this region and important physics in this region. And I will show you maybe tomorrow how we get to this. So, and then we started. And there were many ideas. Some were crazy, some were quite interested. At Brookhaven, we thought about a detector which we called BEAST. In Argonne, they thought about a detector which was topside. Topside was very inspired by ILD and high energy physics. It had it didn't work because it had a 5D colorimeter, which alone probably cost $1 billion. It was just not fundable. It was just enormous, but it was neat. JLab had also their ideas. And then there was an idea of when Phoenix stopped and was dismantled, there was S-Phoenix, the successor of Phoenix. And there was the idea, hey, we could build it such that maybe it can also do electrons. Turns out no, because heavy ions and DIS are very different processes and have very different requirements. It's like you want to make a sorbet on a grill, you know, it just doesn't work. And this is the detector as it came out of the yellow report. Interestingly, it has a TPC, which we then threw out, but nevertheless. So you can see there's a lot of work is going into all this. And this was done by the EPIC collaboration. This is it. We are huge now. We have over 1,000 members. We have 177 institutions, and we are from 26 countries. We are quite everywhere, almost, even in Africa. So our last meeting was in Frascati in Rome. It was very nice, very rainy. Yeah. So this is now the latest EPIC. This is how EPIC is. This is the baseline of EPIC. And I want to stop here because I continue the rest of this then tomorrow.
Thank you, Thomas.
Yep.
Questions, comments? Been waiting for this. Go ahead.
For the, sorry, I'm thinking, on the hadron going
Yeah.
way, yeah, so like, I guess, so there's this big X. When you talk about the PID for, hadrons,
Yeah.
is it that tough that's gonna do the most of it? But then, okay, so,
And here we have to go back. This plot is really
because I guess when I think of the
Yeah.
hadronic calorimeter, I think more of the energy deposited than a PID thing, but
Yeah.
maybe I'm not thinking about.
no. So this is actually a really good plot.
Mhm.
This was made by Lippmann in 2000. Thanks for doing that. And you see the time of flight. Let's say be realistic. The reality sits somewhere in between here.
Right.
So we have probably time of flight has to sit at most a meter. Right now it's 64 centimeters, which is somewhere here. So you can see time of flight only gets you to 1 or 2. If you want to go to 50, you sit here. All you can do is gas. That's all you have.
I guess,
And calorimetry for hadrons, as I said, take a resolution of 50%. That's not great.
I guess I'm thinking for the stuff where you were showing the different processes.
Yeah.
And you want to measure, I mean, not just the electron, that one. Oh, sorry.
That's okay.
You're going to.
No, I screwed up.
It's okay. But where you were talking about where you actually want to be able to measure.
Yes,
Identify
yes.
the whatever happened to.
That is
the
in CDIS.
vision stuff.
That's in CDIS or
Yeah.
in, of course, exclusive. This is the
Right.
very
So
extreme.
then how would you actually do the PID, right? Because that one. So you see. if
In
we-
my PID talk, I will show you what we cover. We are covering. Sorry. So what we are covering is roughly from -3.5 to 3.5.
Yeah.
So that's 4 pi. It's not 4 pi, okay? But there's a limit because at some point you end up in the beam.
Right.
Okay. We are working on this, and I will show you tomorrow when I start. There are solutions to work on this too. There are off momentum detectors and Roman pods, Jacoul detectors, which sit in the beam.
But I think of them as more like scintillator, and then I can get energy fast. Okay, maybe
Now,
not.
scintillators are not, a scintillator I know alone doesn't give you
Right.
energy.
Okay, okay, maybe.
So hadron calorimeters have scintillators, but they're stacked, right? They are sampling. So you have iron scintillator, iron. You know it from the calorimeter you guys are engaged.
You were talking that you were like for electrons they were planning to remove magnetic field because of bending will produce synchron.
No, we don't.
No,
Magnet-
not for EPIC. Just
Yeah.
if it happens, how will you distinguish between photon and electrons?
Between photons and electrons, that you do. Because and photon doesn't have a track. In the tracking, you don't see anything. You see in the electromagnetic. In the electromagnetic calorimeter, you see a shower ahead, and you see nothing before. So it has to be a photon. If you have a track, electron. Well, how you do electron is, of course, a little bit tricky. So typically that is done with calorimeters, very good calorimeters, or transition radiation detectors. But and I will show you that all our PID detectors also provide some means of measuring electrons. So it is a combined force of everything, because think about it. What our requirement is that we have to have a purity for the electron of 10 to the 4, which means there can be only one misidentified electron in 10,000 electrons. The reason is, if we want to get our structure functions from the scattered electron to Fred, who uses his X filter, we want to make sure that he's not looking at scattered pions or something, but really at the scattered electron. So purity is really essential because it destroys all these cross sections, or it increases the error.
But pi zero might also decay to gamma gamma.
Pi zero, you get to gamma gamma.
Then
but-
again, it will be like.
So yeah, pi zeros are actually important because we use pi zeros. For example, you can use pi zeros to calibrate a calorimeter. It's actually quite nice. So what you do is, let's say you have the calorimeter and you don't know the calibration, you have no clue. You're a complete idiot, okay? So the pi zero goes to gamma gamma. And then you measure gamma gamma and you look at the invariant mass of the system, right? And then you start to minimize your calibration until the peak is actually where the mass of the pi zero is. And then you play around further until this peak gets sharper and sharper. That's what you do. This is how you can calibrate a calorimeter. This could be actually a nice AI algorithm or machine learning, right?
The electron, I guess I'm thinking in terms of what gets produced in the interactions and distinguishing what was E prime, the
Yeah,
recoil versus
yeah.
other
I
stuff
know,
that you've made.
I know.
Is it the
We-
direction?
yeah.
Thing?
So
Sorry.
that is why I know where you're going. So it is true. Think about this process, right? I mean, which is Tobias's prototype. Diffraction, and you get a J psi.
Right.
And the J psi comes to E plus E minus, and suddenly you have two electrons in the game. Which one is which? Okay. And we were initially nervous, and that is why people came to us and said, why don't you use muons? You only look at muons. Because if you look at mu plus mu minus, you identify the muons, you know that the only electron in the game must be the scattered electron. But it is actually not so bad. The contamination, because what you need is for that, for the E plus E minus, look, you look at the invariant mass of the J psi, right? And you have to ask, how often does it happen that the scattered electron plus the positron just gives the J psi mass? And that probability is really tiny. So that's not the problem. However, there might be other processes. I don't, say that. But I'm confident Harvard did it. And yeah, I mean, the good thing is, you know the direction. Most of the electrons which are coming from decays or something are going in the forward direction, while the electron is more measured in the backward direction. So just to completely confuse you, and it confused me all the time, in a DIS, if you have an electron coming in and the hadron going in, the forward region is where the hadrons go, and the backward region is where the electron goes. I would have always done it differently, but Harold did it this way, and that's it. Once somebody makes this rule up, follow it.
All rings will have like the same energy.
What? Sorry.
All rings. I mean, the ring for
Yeah.
the electron and for the positron will have the same energy. I think. I mean,
No.
it will be different.
Oh, yeah. So the electron ring has 18 GeV maximum, and the hadron ring will have protons with 275 G. So the reason is you cannot go much higher than this, maybe 20, but then you're pushing it. And the reason because is the synchrotron radiation. You bend an electron and it just radiates off. And that is also why, which is interesting, if you look, for example, at the luminosity you produce versus the energy, the highest energy, if you run 18 on 275, is sitting here, while if you go, this is, yeah, if this is whatever, 10 on 100, and this is 18 on 275. No, so the other way around. So the maximum luminosity you get for 10 on 200, something around it, or 275. The hadron doesn't measure. But the moment you go to 18 plus 275, we go down because the 30 megawatt limit sets in. They don't want to exceed the 30 megawatt synchrotron radiation. And if you would crank up the luminosity here, you exceed that. That's a self-imposed limit.
So, yeah, in that sense, I was thinking about if there is a clear asymmetry in terms of the energy. So there is a preferential direction of.
There is a boost in the side.
There is a boost. So in that sense, the detector has this into account as well.
Yes, and the detector, if you look at it, is very asymmetric.
Okay.
So all the hadron capabilities are in one corner, pushed.
So I know that because the beams aren't collinear, you have this crossing angle, and then you need these crab cavities. Does that not contribute to the synchrotron radiation?
No. So for those of you, I somewhere have slides. So I think
About the.
Christoph is coming, right? Yeah. So for those of you who don't know, as I said, at hadron colliders, there are magnets which make it possible that you have zero crossing angle. They really collide with, head on like this. As I told you, we don't want to touch the electrons. So they are straight, but we have to get the hadrons in. So there's a crossing angle. That crossing angle is in the order of 30 millirad. Now, there's a problem. How can I, here. So the beams are bunched. These are the hadrons, these are the electrons, okay? And now they have a crossing angle, and I exaggerate now, and they go through each other. And what you see is that they only see a small fraction of the whole bunch. If they cross here, they really overlap fully. They go through each other. But if they do this, there's not much. So the ingenious idea is what is called crab crossing. This was not really done so far in Great Glory. I think at Keck in Japan, they had that. So what they do is they give an EM radio frequency cut. And what they do is they bend them like this. And then they overlap. And once they are through each other, then you bend them back so that they go this way. So essentially you tilt for the moment shortly before the collision, you tilt the bunch in the beam. This is done with radio frequency. And that is pretty tricky, and we hope it works. That's a question you should ask, Chris. And that is called crab crossing because I think it looks like crabs.
Bending is so small that it doesn't cause the synchrotron.
I mean, we are looking at this right now. We have worries about two kinds of backgrounds. The one is synchrotron radiation, which still happens at these things. The other is hadron beam gas events. So this is a funny thing. Even if you have the best vacuum, the beam pipe, evaporates electrons or whatever. Now you have hadron beam or electron beam coming on, which collide with these electrons. And these are little collisions. It's like you have suddenly, if it's a proton which comes out of a beam pipe colliding with a proton, you have a little proton-proton collision. That makes real tracks. This is a problem. What the ingenious idea of Christoph Montag and others, you have to ask him about this, is this outbaking. So what they do is, before the run, before we start running, they bake the beam pipe to very high degrees, very hot. And that will kind of evaporate, and outgas everything. That, of course, freaks the people out who built the silicon detector, because the silicon detector was supposed to sit very close to the beam, but the temperature of this was so high that it would kind of smoke this thing. Now, we cannot move the detector easily in and out. We have 26 systems. It's a complex thing. Once this thing is in, this thing is in. So what we had to do is we had to move the silicon detector further out so that they can bake this beam pipe. It does not, I don't melt our silicon. Yeah. I come to this at the beginning of. Next step.
That's
quarter of work?
Yep.
Yeah, 2:45.